So what is that we are designing now? What is that we are looking at? We are looking at designing a binary mod counter. Okay, we want to design a binary mod counter. Now in order to do that design, we have taken a specific example, and in that example I'm saying that I want to design a mod 6 counter. Okay, and whenever we talk about a mod 6 counter, it need not be always a 0 to 5 only. That is, it will count 0, 1, 2, 3, 4, 5. So altogether there are 6 unique states. So I call it as a mod 6 counter, right? It need not be. When I call it as a mod 6 counter, it need not be having a sequence. Okay, it need not be a counting sequence. Instead, any 6 unique states. Okay, if that counter is counting any 6 unique states, then I call it as a mod 6 counter. Similarly, if I want to design a mod 8 counter, then what I am expecting? It need not be 0 to 7. Instead, any 8 unique states, if it is counting, then I call it as a mod 8 counter. Okay, so that's why even I call my counter as a pattern generator. A specific pattern has been generated. So I can say, okay, as a designer, now I say that I want to design a counter. I want to design a mod 6 counter. Okay, and this mod 6 counter is giving me a sequence 0, 2, 3, 6, 5 and 1. Okay, so what's the counting sequence I want now? See, my sequence is not sequential. It's not 0, 1, 2, 3, 4, 5. Instead, I have 6 specific unique states now. 0 is one state, 2 is another state, 3 is another, 6, 5 and 1. So there are 6 different states, but they are not in a sequential way. Okay, so this is a pattern I want to generate. I want to generate this pattern. So I want to design a mod 6 counter which is generating the pattern 0, 2, 3, 6, 5, 1. Okay, so this is my design. So what do you mean by generating a count 0, 5, 0, 2, 3, 6, 5, 1? Okay, now tell me how many flip-flops I require. So the first thing for design is I need to know the number of flip-flops. I want to count this sequence. Tell me how many flip-flops are required. Yes, Sinchana, correct. It is 3 flip-flops, right? Why 3 flip-flops? How do I going to identify it? Number 1, I want to design a mod 6 counter. So as it is 6 stages, it is sufficient to do it with a 3 flip-flops. That's the one thing. The second thing I look at, what's the count sequence, the maximum number. In my count sequence, which is the maximum number I have, the maximum highest number is 6. So in order to represent this 6, how many bits are required? 3 bits are sufficient. So I will design a 3-bit counter. If suppose, if I have a case wherein I say instead of 6, if it becomes 8. 0, 2, 3, 8, 5, 1. If this is my counting sequence, tell me how many flip-flops are required. Tell me how many flip-flops are required. Yes, Tanya, it's correct. I require 4 flip-flops. Why 4 flip-flops? What's the highest number I am counting here? The highest number is 8. And in order to represent 8, how many binary bits are required? 4 bits are required. It is 1, 0, 0, 0. That forms 8, right? So I want 4 flip-flops. So that's why I'm taking 4 flip-flops there, right? So you have to look at the highest number you have in that sequence, then decide how many number of flip-flops are required. Okay, so in this case, how many flip-flops are required for me? I require 3 flip-flops. Now, how do I connect it? Which type of flip-flop I have to use? Whenever we talk about the counter design, I can design a counter using any flip-flop. It may be JK, T, D or SR. Okay, I can design it using any flip-flop. So if you have not given a if it is not specifically told which flip-flop to be used, you can always make use of a D flip-flop because it's a sequence. So So what's the type of flip-flop I'll be using? I can use any flip-flop. Okay. And which flip-flop to be used, that needs to be specified. Which flip-flop to be used, that needs to be specified. If it is not specified in the question, if it is not asked which flip-flop you are supposed to use for designing, then always you can go with why D flip-flop? It's because it's the simplest flip-flop can be used for the design. Okay, so I can go for a D flip-flop. Or usually in a question, it will be specified we have to use which flip-flop. Okay, now the next question is how to design it. Let us go with a general block diagram. So whenever I talk about the designing of a counter, how do I design a counter? Counter has to count a given sequence. What's the sequence I need to count? If it's a sequential way, it will be simple. But whenever I am given with a specific pattern and I have to count only that pattern, then I should adopt some control logic along with my flip-flops to design particular pattern. Okay. So what happens to my block diagram? So as I want a mod 6 counter, I want 3 flip-flops. So let me write the generalized diagram now. So I'm writing. Okay, let me start with a JK. I choose a JK flip-flop. So I'm designing a 3-bit counter, right? So it's a mod 6 counter. So I'm designing 3. So I'll consider it as a JK flip-flop. Using the JK flip-flop, I'm going to do the design. So let me put it like this. Now, flip-flops are used for generating the states, right? From one state, if I want to go to the next state, then the flip-flops are used. Flip-flops are used to transit from one state to the another state. For that purpose, I am using a flip-flop, right? But what is my previous state and what should be my next state? That will be decided based on the control logic. So let me write the control logic. So this control logic is going to tell me what sequence, what should be the first state. If it is 0 is my first state, my second state should be 2. Now how do I make my state from moving from 0 to 2? So that will be decided by my control logic. So this is the control logic I have designed. So that control logic will be giving me the inputs. Okay, so this is my JK. J1 K1, J2 K2, J3. Okay. Now this will be giving me an output. No? So let me call this as Q1, Q1 bar, Q2, Q2 bar, Q3, Q3 bar. Okay. Now this outputs whatever I am having, that will be again given back to my control logic. Why? Because this is going to decide my next states, right? Of course, I have a clock. Let me take an negative edge trigger. This is the general structure of a mod 6 counter. What is that I have done? I have chosen JK flip-flops. How many JK flip-flops are required? 3 JK flip-flops are required. So I have chosen 3 JK flip-flops. Now, what's the pattern I need to generate? It was 0, 2, 3, 6, 5, 1. So from 0, I want to move to the next state. So if it is 0, if I want to generate my output to be 0, what's the input I am supposed to give to my J and K? So that will be decided by my control logic and it will give an input. To that input accordingly it will be getting an output. So that output will be again given back to the control logic. so that the control logic is going to decide what will be my next state. Okay, so from 0 to 2, if I want to move, if 0 is my output, that output will be again given to the control logic, so that the control logic will make my next state to go to 2. So control logic is a heart of my design. This is a general structure. What is my flip-flops are doing? They are generating the count. But what should be the count of the previous state and what should be the count of the next state? That will be decided by my control logic. So what is our agenda now? Our agenda is to design this control logic. So whenever you are given with a counter design, what is that? You have to decide first. You have to decide what is the counting sequence. So I have given with this counting sequence. So in order to get this counting sequence, how many flip-flops are required? I will decide that, and that will be taken. And then if it is not, if it is specified, then you have to use that specific type of flip-flop. If it is not specified, then you can always use a D flip-flop. Okay, then I'll be going for the generalized block diagram using the JK flip-flop. 3 JK flip-flops I want to design my mod 6 counter. So I'll be taking an input from the control logic in order to generate the present state. Then the output of the present state will be again given back to the control logic to generate the next state. Okay, so this is the general block diagram we are having for designing of a mod 6 counter. Any doubts? So now what is our agenda? Our agenda is to design the control logic. In order to design this control logic, we are going to look into, we are going to form a different types of tables. Okay, what are the different type of tables we will be going through? Is one is called excitation table. I will be going through a table called as an excitation table. Okay, so what do you mean by an excitation table? We'll learn. And one more type of table is called application table. These are the two types of table we'll be making use for designing of a mod 6 counter. What are the two types of tables we are taking use of? It's called an excitation table and the application table. Now, what do you mean by an excitation table? Excitation table is going to tell me, suppose if I have this present state and I should go to the next state. In order to go to that next state, what is the input I am supposed to feed into my flip-flop so that it will be going to that state? That is called an excitation table. Let me make it clear. What is this? I have the count sequence 0, 2, 3, 6, 5, 1, right? Let me write it. So I have 3 flip-flops. So it is Q1, Q2 and Q3. Correct? So my first state was 0, 0, 0. So let me write it. This is present state. So the next state. We have two types of states. One is called present state, the other one is the next state. Correct? So my sequence was 0. So if my present state is 0, 0, 0, tell me what should be the next state. What will be the next state? 2 is the next state, right? So that is nothing but Q1 plus, Q2 plus, Q3 plus. So it will be 0, 1, 0 is the next state. If my present state is 0, 1, 0, what will be the next state? According to this example, what should be the next state? Yes? What happened? What will be the next state?
0, 1, 1.
0, 1, 1 will be the next state, right? So it will be 0, 1, 1. If 0, 1, 1 is the present state, that is 3 is the present state, what should be the next state? 1, 1, 0 should be the next state, that is 6. Then, if 1, 1, 0 is my present state, what should be the next state? 1, 0, 1, that is 5. If 5 is my present state, what should be my next state? 0, 0, 1, that is 1 is the next state. If 0, 0, 1 is my next state, present state, then what should be the next state? Yes, tell me. In this particular example, if this is my present state, What will be the next state? 0, 0, 1 is the present state. What will be the next state?
0, 0,
0, 0, 0. Correct. Right? That means I'm generating a sequence like this, no? 0 was my first state, then it was 2, 3, 6, 5, 1. Right? This is what I'm doing. From 0, I'm going to 2. From 2, I'm going to 3. From 3 to 6. 6 to 5. 5 to 1. And 1 going back to 0. So this is the sequence I want to generate. So if this is my present state, then I expect my next state to be this. Right? Now, listen carefully. I'm in a present state 0, 0, 0. And I want to go to the next state 0, 1, 0. Correct? And in order to transit from one state to another state, which flip-flop I am making use? I am making use of a JK flip-flop. So, what my excitation table is going to tell me is, what is the input I am supposed to give to my J and K in order to excite from the given present state to the given next state. In this example specifically, what is the input I am supposed to give to my J and K in order to jump from the state 0 to the next state 2? What is the input I am supposed to give to my J and K to jump from 2 to 3? What's the input I am supposed to give to my J and K to jump from 3 to 6? Jumping is called excitation here. Excitation from 0 to 2. What's the input I'm supposed to give to my J and K flip-flops so that it will be exciting or jumping from its present state 0 to the next state 2? What is the input I'm supposed to give to my J and K flip-flop so that it will be moving from the state 2 to 3? In order to move from the state 3 to 5, 6, what's the input I'm supposed to give? In order to move from 6 to 5, what's the input I'm supposed to give? So these things will be told by what? That will be given from the excitation table. Why I call it as an excitation table? I call it as an excitation table because this is the table which is going to tell me what is the input I'm supposed to give to my flip-flops to excite to the next state, the given specific next state. So that is called an excitation table. Is this clear? What is excitation table? We need to build an excitation table for every flip-flop. Okay, we'll do that. But have you understood what do you mean by an excitation table? Is this clear? Any doubts? What do you have next here? Is this clear? Similarly, you have one more table called as an application table. Okay. What do you mean by an application table? The application table will be giving me, in order to get the specific pattern of output, what's the input? What are the different inputs I can apply to my JK? Okay, so that is called an application table. Application table tells me, in order to get a specific output, what possible inputs I can give for a particular flip-flop. Application table is again built for a particular flip-flop. Excitation table is also built for a particular flip-flop. Now I have taken a flip-flop and I want a particular output to come from the flip-flop. In order to get that output, what possible inputs I can give? That is called as an application table. Okay. So, in the next class, we will build the application table, excitation table, and build one of the counter. Okay, using a JK. And in the same way, I want you people to build your T and D flip-flop based counters. Okay, that will be an assignment for you people. Notes.